In today's lesson, we're going to look at rational exponents. If you remember what a rational number is, it's a number that can be written as a fraction. So we're looking at exponents that can be written in fraction form. So in order to understand how they work, I've got a couple of examples. And rational exponents work in such a way so that all of the exponent rules, everything you've ever learned about exponents so far, still hold the same. Okay, so if you think about 5 to the power of 1/2, so we're trying to see what happens if we square 5 to the power of 1/2. If you use the power of a power rule, so we've got an exponent of an exponent, that would mean we multiply those exponents. So the exponent would be 1/2 times 2. Well, 1/2 of 2 is 1, so that would be 5 to the power of 1, which gives us 5. Also, if we look at squaring instead the square root of 5, that would give us square root of 5 times the square root of 5, which gives us the square root of 25, which is 5. See how both of these, when we square them, give us a result of 5. So we can say that 5 to the 1/2 is equal to the square root of 5. So that gives us our definition of what a rational exponent means. If the nth root of a represents a real number where n is greater than or equal to 2 and it's an integer, or I guess if it's greater than or equal to 2, it would also be a whole number or a natural number, then a to the 1 over n is equal to the nth root of a. So that means a to the 1/3 is equal to the cubed root of a to the 1/4 is equal to the 4th root of a. Okay, so the exponent, the denominator of the exponent, ends up giving which root it is, which is called the index of the radical. Okay, and remember that the number under the radical sign is called the radicand. Okay, so the denominator of the fraction gives us the index, so it tells us what the root is. Okay, and also we could think about a negative fraction exponent, so a to the negative 1 over n would be the same as 1 over a to the positive 1 over n, which would be 1 over the nth root of a. So long as a does not equal 0, since we can never divide by 0 and have a defined number. So if we look at 36 to the power of 1/2, that gives us the square root of 36, which is 6. 81 to the 1/4 gives us the 4th root of 81, which is 3, because 3 to the power of 4 is 81. Negative 32 to the 1/5 will be negative, because that negative is not in brackets with a 32, just leave it out front. So negative 32 to the 1/5 will be negative the 5th root of 32, which is 2. And again, the perfect cubes and fourths and fifths, you'll see on page 52 of your textbook, a nice chart in the margin there that will tell you the ones that you should know. And here the negative is in brackets, so that will be the cubed root of negative 64, which will give us negative 4, because negative 4 to the power of 3 gives us negative 64. And E, we've got the negative exponent. So this will give us 1 over 125 to the 1/3, which will give us 1 over the cubed root of 125, which gives us 1 over 5. Okay, so those are the beginning of rational exponents. But those were all exponents with 1 over a number. What if we have a numerator other than 1? So for example, we've got x to the power of 2/3. Well, there's a couple of ways that we could think of that. We could think of that as x to the 1/3 squared, because 1/3 times 2 gives us 2/3. Well, x to the 1/3 is the cubed root of x all squared then. Or we could think of x to the 2/3 as x squared to the 1/3, because 2 times 1/3 gives us 2/3. So that's the cubed root of x squared. So these things are all equal to each other. So x to the 2/3 is equal to the cubed root of x squared, which is equal to the cubed root of x squared. Note that the denominator becomes the index of the radical and the numerator becomes the exponent. So the top number becomes the exponent, the bottom number becomes the index. Okay? In this case, we're taking the root first and then squaring. In this case, we're squaring first and then taking the root. Either way, we get the same answer. You'll see that as we simplify rational exponents in this form, you'll see that it really becomes more preferred, this method here, where we're using the doing the nth root first, becomes the preferred because what we do is working with smaller numbers. Rather than putting something to an exponent first, as in this case, we're doing the exponent first and then taking the root. We could end up with very large numbers and it's harder to do the root of those. Okay? So this method, a to the power of m over n, equals the nth root of a to the power of m. Okay, this is the preferred use for it. This is equally valid and equally correct. So let's look at a couple of examples of this. So here's one, 8 to the power of 2/3. Okay, so that's going to be, let's do the root first, the cubed root of 8 squared. So we take the denominator becomes the index and the numerator becomes the exponent. The cubed root of 8 is 2 squared, which gives us 4. We'll call that one letter A, and here's letter B. We've got 16 to the 3/2. So that will be the denominator is the index, so a denominator of 2 gives us a square root. So that gives us the square root of 16 cubed. The square root of 16 is 4 cubed, gives us 64. Notice that here the exponent, in this case the exponent is less than 1 and we end up with a smaller number. Here the exponent is greater than 1 and we end up with a larger number. That totally makes sense with what we've been doing before with exponents. And a third example here, I've got 81 to the negative 3/4. So that'll be 1 over 81 to the positive 3/4. So it'll be 1 over the 4th root of 81 cubed. So that'll be 1 over, the 4th root of 81 is 3 cubed, which is 1 over 27. Okay. Sorry, while I try to, excuse me, while I try to flip to a new page here. This should do it here. All right. So simplifying rational exponents. Now I've lost my ability to write. Hang on. There we go. Simplifying rational exponents. And again, the rules are going to be the same as what we've experienced before with exponent rules and with radicals. So if I have 3 to the 3 times x to the 2/3 times 5x to the 1/2, I could take the coefficients and multiply them to get 15, and I can take the exponents on x and add them together. So I'll have 2/3 plus 1/2. So off to the side, I'll do my 2/3 plus 1/2, which will be 4/6 plus 3/6, which will be 7/6. So I've got 15 times x to the 7/6. And a second example, I've got 42x to the 5/3 divided by 28x to the 2/3. And if I simplify that, 14 goes into 28 twice and into 42 3 times. So I've got 3 over 2 as far as my coefficients go. And then I've got, for my x, I've got 5/3 take away 2/3, which is 3/3. So that'll be x to the power of 1. So 3/2 times x. Or you could write that as 3x over 2. These are both the same and both equally good. Okay, so simplifying rational exponents follow the same rules as with the rules of exponents, okay? Just write that once more just to emphasize that. All right, and one more little skill to learn with roots, and that is reducing the index of a radical. So it's part of the simplifying process. So reducing the index of a radical. Remember, the index is the root for it. So for instance, if I needed to simplify the 10th root of, whoops, that doesn't look very good. If I have to simplify the 10th root of x to the power of 5, it might be useful to turn that into a fraction exponent first. Remember, the exponent is the numerator and the index is the denominator. Oh, well, 5/10 is equal to 1/2. So that's equal to x to the power of 1/2, which is the square root of x. So this is a simplified version of the original. By reducing the index here, we've gotten rid of lots of those exponents, and it's a much simpler form. Let's do one more example like this, where I'm taking the 4th root of x to the power of 12. Turn it into a fraction exponent, so I've got x to the power of 12 over 4, which is 12 divided by 4 is 3, x cubed. And that's it for this lesson, and I hope you had lots of fun with it.